Right, we're back for a short encore on infrared spectroscopy and Raman and handheld devices. Again, there's some good learn sci resources linked in Blackboard, and you should look at these in your own time. Some good stuff in infrared. The infrared region is divided into three sub-regions: the near, the mid and the far infrared, and with the near infrared being closer to visible light. They're all used in analytical terms, like all of the electromagnetic spectrum. This is how it works. Again, in the Learn Sci resources, some videos on this. When infrared radiation interacts with molecules, it produces a range of molecular motions, including stretches and bends, and these are characteristic of the molecule absorbing the radiation and produce what's called a fingerprint. So we have symmetric stretching, anti-symmetric stretching, and bending and scissoring. You can try doing this as sort of mildly aerobic exercises if you want, just to help you memorize stuff. So here's a typical IR spectrum, in this case of hexanoic acid, also known as caproic acid, which is a naturally occurring fatty acid with an odour redolent of goats. Appears in all sorts of things. It's one of the smell components of vanilla, for example. Notice a broad peak around 3000. This is very characteristic of OH groups. It is also seen in samples that contain water. This peak broadening is caused by hydrogen bonding. Samples contain, just moving on from the fingerprint, there's lots of other methods which use infrared. Samples contain a range of food pathogens absorb infrared in characteristic ways. This can be useful in diagnosis, so there's examples there of the absorption of the fingerprints of different food poisoning pathogens. And over here is a paper looking at how classifying food pathogens based on near-infrared laser scattering. So if you click on the image here, it'll give you some background reading. It's not examinable, it's just general background reading. We can use it in other ways as well. If looking at black over Wilf smothers is a thing that people in Durham say when the weather's getting worse. And of course we can access weather information in real time from all over the world. Infrared satellite images are used widely for weather monitoring and forecasting. The data is freely available and updated every 10 minutes. If you click on the lower link for the website or the map view link to see the world right now, if it's cloudy day, it might be a bit hard to see where we are. Okay, just for fun, here is the world weather in real time, updated every 10 minutes. Okay, get rid of that. Nice, moving on. So it's widely used for weather forecasting and monitoring, but it's also used for other things as well. Plants absorb light in both visible and infrared regions, and satellite imaging can be used to identify vegetation and monitor plant health, as well as other insights such as tracking deforestation. So the graph there is an example of different crops and their different infrared absorptions. And over here we're going to link to digital.dai for an example of remote sensing of vegetation in Nepal. So quite exciting stuff these days. We can get information from all around the world. Portable devices come into widespread use. See this paper linked here for a proposal for a low-cost handheld device to get information on plant status in the field. It's going to be a big thing in the future. I'm fairly sure of this. As well as scientific interest, there is also the taking of photographs using cameras adapted to use infrared rather than visible light. Some striking images may be produced this way, and this is one of the things I personally want to have a look at. So it looks like you get some interesting and fun images out of this. Okay, just to finish off, we'll talk about Raman scattering, which links directly into handheld devices. There's devices coming on the market now using Raman infrared spectroscopy, most focus on a particular molecule, perhaps measuring, for example, lycopene in tomatoes. So the red molecule is characteristic of the colour of tomatoes. This is how it works. Again, there's lots of resources you can read about Raman. Essentially uses something called scattered radiation. When infrared passes through a sample, the vast majority of the radiation is either reflected, transmitted or absorbed. A very tiny proportion, 1 part in 10 million, is scattered, and this is used in Raman, sometimes called Stokes-Raman scattering. It happens at a range of frequencies which are characteristic of the carbon skeleton of the molecule involved. So it's not interested in functional groups, it's just the links of carbon atoms in the skeleton. This video reviews the process. It does have annoying music. But other than that, it's not a bad video. It's well worth having a look at, and it will explain it in a reasonable amount of detail. Okay. So we've got a couple of images here. In the first image, the Raman scattered light is down in this region. It's massively hidden by the main absorption, which is way off up the top of the screen, extending a long way up. But if we apply a filter, the Raman fingerprint, again characteristic of the carbon skeleton molecule involved, can be measured and is characteristic. Again, it's said to be a fingerprint of the particular molecule involved. So here's an example. Raman can get very complicated, so typically databases of known compounds are used. They may be linked to expert systems to help the analysis. If you look on the image down here, there's an example of Raman used in the analysis of edible oils. Okay, so just to reiterate the point about the carbon skeleton, here's the Raman fingerprint for the most simple carbon molecule possible, diamond, which contains just carbon. It's a single peak. Whereas that for polystyrene, which is not a particularly complicated molecule, it uses repeated units, has a much more complicated Raman spectrum. Okay, there's a couple of videos to suggest how quickly the technology is developing. Review them yourself. I don't think we've quite reached the point where the claims that are being made in the second video are substantiated by the techniques that are available. But there we are. Okay, just one last thing. And finally, why is video added to the water for poaching eggs? I'm sure many of you work this out straight away. It lowers the pH, so promoting denaturation of the egg proteins. This tends to make the outer layer of the poaching eggs stick together a little bit better, helping the production of a nice poached egg. So there we are. That completes lecture 7. Thanks for listening.